Today's lecture will be on which is more soluble sample problems from our solubility unit of chemistry. The first type of problem we're going to deal with is when you have the same number of ions being produced. You can see the sample problem we have up on the board are all sulfides, and these sulfides all produce the same number of ions per compound dissolved. Just so you have a sense of this, I won't write all four reactions up on the board, but you can see the first one, we produce 2 ions. Then the second one, we also produce 2 ions, etc., as you go down the rest of this list here. So the idea is when you produce the same number of ions, you can rank the KSPs in order based off of the value of the KSP. Most soluble we're going to list with number 1, and least soluble we're going to list with number 4. Really, you don't even have to look at the coefficients. You can look just at the exponents, knowing 10 to the negative 13th versus 10 to the negative 45th. The most soluble substance is going to be the MnS, and the least soluble substance will be the copper 2 sulfide. Then the two in the middle, we've got 10 to the negative 22nd and 10 to the negative 28th. So then we'll have 10 to the negative 22nd for the cobalt 2 sulfide, and then lastly the cadmium sulfide will be the third most soluble of the substances there. Once again, you use this method when the number of ions produced is the same. Now, the second method we have is for when the number of ions produced are different. So we've got two problems here. We've got silver chloride. When it breaks apart, you're going to have silver ions and chloride ions. And over here, we've got silver phosphate. When it breaks apart, you will also produce silver ions and phosphate ions. The number of ions produced from silver phosphate is 4. The number of ions produced from silver chloride is just simply 2. So we can't do a direct comparison of the KSP values like we were able to do in the previous problem. We need to go ahead and solve for the solubility of each of these substances and then compare the two solubility values. Whichever number is higher, that will ultimately be the more soluble of the two substances. The next step will be to solve a mini ice problem. We're going to let X equal the change. So for every one of the silver phosphate that dissolves, you're going to increase your concentration of silver ions by 3x and increase the phosphate concentration by x. Same thing on this side. We have let X equal the change. So when silver ions are produced from silver chloride, that'll increase by a concentration of x, and so will the chloride concentrations. I'm going to write a KSP expression for each one of these. We have a KSP equals concentration of the silver ions times the concentration of the chloride ions. And then over here, we're going to have the KSP equals the concentration of the silver ions cubed times the concentration of the phosphate ions, like so. We're going to plug the X in for these statements here. So then we're going to have our KSP value given up above, 1.77 times 10 to the minus 10th equals X times X. And then over here we're going to have 8.89 times 10 to the minus 17th equals 3x cubed times X. If we simplify, we're going to have 8.89 times 10 to the minus 17th equals 27x to the 4th. And over here we have just 1.77 times 10 to the minus 10th equals x squared. Solve for x, and I get 1.33 times 10 to the minus 5th molar. And then I solve for x over here, 4.26 times 10 to the minus 5th molar. It's one of those rare instances where not only are the exponents the same, you've got to look at the coefficients. Since 4.26 is a larger value than 1.33, Ag3PO4 is more soluble. And that's because it ultimately has a larger X value.